Hi, welcome to today's PhET lab on projectile motion. In this lab we want to verify the kinetic description of projectile motion. That is, we want to verify that these equations, here we're shown right here, 6 equations, accurately describe motion of a projectile once it's been launched, or in our case fired from a PhET cannon. So these equations describe projectile motion. We've actually already derived the vertical component of the projectile motion in a previous lab on free fall. We derived the equations of motion for projectile free falling, that is just dropping straight down, neglecting air resistance. The equations of free fall would be given by the equations that we have right here for the vertical component, that is the y component of the motion. So for the y component of the motion, we would have the velocity is whatever it starts off with, and if you drop it, that would be 0. In free fall, a lot of times we drop stuff, but it could be thrown up or down, and so some have some initial component of velocity in the y direction. So the y velocity is whatever it starts off with, vy0, minus gt, and minus gt tells you how the velocity is changing because it's being accelerated down due to the action of gravity. And the y position, we derive this equation for the y position in free fall would be whatever the initial position is. So y is, when you start the clock, t equals 0, y is wherever it starts off at, plus how it acts due to the y velocity, so the initial y velocity times time, and minus 1/2 gt squared. So this minus 1/2 gt squared is the action of gravity, bringing it down. Here's g is acceleration due to gravity, and this makes its position go downward in the negative direction. So we derived that. If you want to see the derivation, you could go back or check the textbook, go back and look at the video where we derived it. Now the motion in this case, in projectile motion, is just a little more complicated. So like I say, we could say here, if this is William Tell or whoever this is, he shoots a bow, he shoots an arrow with his bow, and that arrow flies. It's a projectile flying in projectile motion. That arrow now is not just in free fall because it's got an x component of its motion. It has a y component. If it was just, we would call it free fall if he just shot it straight up. If he just shot it straight up, I guess he would know what to do. He would have to run out of the, because if he shot it straight up, it would fly up, turn around, come back, and then he'd have to get out of the way if he didn't want to get hit in the head. So here he's shooting it at an angle, and so it's going to have some initial x and y components of the velocity, and those x and y components of velocity we pick out with trig. The x component is the initial velocity times the cosine of the angle. So you can see here, let's say if the angle was 0, you'd bring this all the way down, then cosine of 0 is 1. All the velocity would be in the x direction. Conversely, if he tilted it up to 90 degrees, cosine of 90 is 0, so there would be no component of velocity in the x direction if you shot it at 90. On the other hand, with y, so if he shoots it at an angle of 0, that is horizontally, sine of 0 is 0, then there's no initial component of y velocity, as you can see here. On the other hand, if you shot it at 90 degrees, sine of 90 is 1, and then all the velocity would be in the y direction in that case. So here, these are the equations for the initial velocity in the x and y direction. The cosine and the sine, pick those out for you because the components of vectors are picked out by these trigonometric functions, as we've seen. So we want to verify that these equations hold true for real projectiles. Well, this being an online lab or virtual lab, whichever case, we're not going to actually shoot real projectiles. We're going to shoot projectiles, virtual projectiles, at the PhET projectile motion field. So that's where we're going to do our experiment here, is in PhET projectile motion field. So here we are in the PhET projectile motion field. Notice I've selected lab. That's what we're going to use. Just select the lab tab. click air resistance on. We're going to use air resistance just to give us a little bit of variation from the kinetic description of projectile motion, where those equations have been derived neglecting air resistance. By adding a little bit of air resistance, we're going to get a little bit of variation, a little bit of experimental error, if you will. But for projectiles like a cannonball and for the tank shell, which you're going to use when you do the experiment, I'm going to use the cannonball as an example, but you're going to use the tank shell in your lab. Again, I'm going to go back to the cannonball for our example. Either one of those is going to act basically like an object that pretty much neglects air resistance. Tank shells and cannonballs are pretty aerodynamic. They basically ignore air resistance to quite a good degree. Well, let's see what the difference would be. So I'll fire it. Now here at PhET Labs, I can fire this thing, PhET Labs projectile motion field. I can fire this thing. I have some tools I can measure stuff with. I can measure the range, and it also tells me what I can measure. So I put it on these different dots. It tells me how far the range, the horizontal range. So right here at time 0.7 seconds, the horizontal range of this thing was 12.57 meters. However, I'm not going to have us use this, so we're not going to use this this particular tool here, this time range height tool. We're just going to use a tape measure. And the reason for that is because if you were to go to a real cannon firing range field, it would be pretty hard to get a stopwatch that you could use that could accurately time the time of flight, or the times that your cannonball or whatever you were shooting, your projectile, would be at different positions. It'd be very hard to get a good thumb action and be right on the spot with your stopwatch to measure those times of flight. So what we're going to assume is all we have is a tape measure, which we could definitely bring to our field with us. So we could measure how far it goes, for sure. With our tape measure, this would be something you could do at a real field, no problem. You take your tape measure out there, your 16.91 meters is the range of this thing. So we shot it at, we can see over here, it was shot at an initial speed of 18 meters per second over here, and from an initial height of 4 meters, and it had a horizontal range of 16.19 meters measured with this tape measure. This thing would be more accurate, okay, whatever that, but we're not going to use that. For our lab, we're just going to pretend that all we got is a tape measure, and this is what we use. So that was with air resistance. What if we turned that off? I'm going to fire it again. Let's say I fire it where there's no air resistance. Well, you could see what happens here. I could basically see no difference. I don't see any difference. In fact, when could I see a difference? So if I shoot this thing, maybe like this, and now you notice that if I shoot this now, it's off the screen. The action's off the screen. So what I do is I click this minus sign here, zoom out. Now I can see what the action looks like. And so here I shot it at this angle from pretty high up. Now we can see the range is 45.3 meters, and that was with no air resistance. Let's shoot it one more time with air resistance and see if there's a difference. See, now there's a slight difference, right? So air resistance is a factor. Okay, so here the range without air resistance, I'm measuring 45.53. With air resistance, 45.09. You can see that this cannonball, to quite a good degree, basically neglects air resistance, or you can ignore air resistance when you're considering projectile motion with this cannon. And the tank shell, I tell you, tank shell's even better than the cannonball at neglecting air resistance, and that's what you're going to use, the tank shell. So the first thing we're going to do when we with our PhET Lab projectile motion experiment is verify the speed that this cannon shoots. Okay, so we see here they tell us it's 18 meters per second is the speed this cannon shoots. So our first job is going to be to verify that. So let's see how we're going to do that. The first thing we want to do to verify the kinetic description of projectile motion is verify that these equations allow us to experimentally determine the initial speed of our PhET cannon. I mean, we know the initial speed of that PhET cannon is V0 is equal to 18 meters per second because we just read it off the screen in FET. But we want to make sure that this known initial speed of 18 meters per second is compatible with this kinetic description of projectile motion. And we're going to do that experimentally just by measuring lengths with the tape measure. So we're going to assume we don't have a stopwatch, and all we can measure are lengths. That is, we can measure the initial height that we fire the projectile from, and then we can measure its range, how far we shoot it downrange from where it gets launched. So to do this, let's get ourselves a coordinate system first off. So there's our x and y coordinates. So let's just figure, and here this is going to be an initial position, x0 equals 0. Generally doing projectile motion problems, you're going to take the initial position, x0, that is where it is when you fire the projectile, to be 0 on the x-axis. You could put it somewhere else, but why not put it to 0? And then in that case, this equation right here will just simplify down to vx0t will be the position of the projectile at any time after you fire it from 0 to t, where the final time would be the time of flight. Well, a little more as we get along here. Let's just think that let's say we shoot it from this initial height up here, y0. Let's say that's where we fire it from, and our cannon, say, is attacks something like this. Okay, has it's not shot horizontally, it's shot up at some angle like that with an initial speed v0. That v0 is a vector. We're going to fire our projectile at an angle like this. Okay, so we're going to fire it from a cannon. We'll do that and it'll go boing, ding, 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 and land down somewhere over here at a position x equal to the range. X equal to range, that's how far it goes. That's how far it has gone horizontally when it hits the ground, x equal range. So now we're going to resolve this velocity vector into its x and y components. We're going to shoot it like that, and like any vector, we can resolve this velocity vector into components. Components along the x direction and components along the y direction. Okay, so we fire our projectile at this angle theta above the horizontal. You can see what that is. The x component of this initial velocity vector, we can see over here, is given by the magnitude of this initial velocity, that is the size of the hypotenuse of this right triangle created by the vector here. So the length of this arrow is the size of the hypotenuse. So the cosine will pick out the x part. This will be vx0 right here, be the length of this side of the triangle, and that's the hypotenuse times the cosine of the angle. And then vy0 will be the vertical part, or the side opposite to the angle. Here's the side adjacent, vx0, here's the side opposite, vy0. Vy0 is v0 sine theta. Okay, so we got that, but what are we looking for here? We're looking to find v0. So how are we going to do that? Well, we're going to be given the range, and we're going to be given the initial height. We'll call it h equal y0. Scroll that off over there. So we're given the range and we're given the initial height. And how do we get those? We're given those, well, we measure them with a tape measure. Just take our tape measure and lay it down there, measure the range, and stick it up this way and measure the height that we shot it from. Okay, and so if this description holds, then let's see if we can figure out what the initial speed should be from these measurements. Okay, so how are we going to do that? What we're going to do that is take a special case of how we fire the projectile. So this was just any old case. What I want to do is take a special case. So what we want to do is use this kinetic description to verify that the initial speed of projectile shot from the cannon is indeed here 18 meters per second, is we want to help ourselves out by setting theta equal to 0. That is, we want to adjust our cannon so it shoots horizontally, like that. So we're going to put v0 like that. And then if this is the case, you can see that okay, like I said, the angle is 0, and that means that the entire velocity is going to get put into the x direction. So in other words, the initial velocity in the x direction, which remains constant, by the way, because what we have is acceleration due to gravity. Our acceleration vector g is just pointing straight down. That's why in our kinetic description of the equations of motion, the position of the projectile x, the horizontal position of the projectile x, after we fire it is just given by where it was when we shot it, here in this case x0, which we're going to set equal to 0, plus the velocity in the x direction times time. And the velocity in the x direction times time is all we need here because that velocity is constant. Since there is no acceleration in the x direction, there is no change of velocity in the x direction after we fire the projectile, because we're neglecting air resistance. If there was air resistance, then this would add some horizontal component of acceleration, and so we would have another term. But neglecting air resistance, which we're doing, and as we saw, we can to quite a good degree of accuracy for projectiles like cannonballs and tank shells, or for even more fluffy projectiles that would normally have a lot of air resistance, like wiffle balls or bouncy balls. If they're not going fast, if you just throw them from, say, from one hand to the other, or just toss it to your friend in a gymnasium or the lab or something like that. For low velocity projectiles, those are also to quite a good degree going to ignore air resistance or be able to neglect air resistance in the kinetic description. And in other words, the kinetic description will give you quite a accurate representation of the projectile motion. Anyhow, we're going to shoot this thing horizontally, and that means in that case the Vx0 will just be V0 at the angle 0, so cosine of 0 is 1, and the Vy0 will be equal to 0. Okay, let's see what that does for us in our equations up here. Okay, so in that case, so our x motion, okay, just from this equation right here, is going to be, okay, Vx0, but here that's 0, and Vx0t, but the Vx0 is, here's Vx0 is just V0. The Vx0 is the speed, is the initial speed. The constant, the speed in the x direction will be constant, and it will be the initial speed that we shoot it at, and then times t. So from the time you launch it, say time t equals 0 to the time it hits the ground, the time of flight, we're going to call that the time of flight, then whatever that is, it's going to hit over here, whatever that time of flight is. If we knew that, then we could just stick that right in here, that time of flight times the initial speed, and that would give us the range, how far the projectile goes horizontally after we shoot it. Okay, so let's see, so we got that. Let's see, well, we're trying to verify, what are we trying to get here? We're trying to verify this V0. So let's say if if I knew that t was equal to that time of flight, I'll just write like this, t is equal to that time of flight, then I would have the range, x would be equal to the range, would be equal to, okay, the V0t at that time, if I knew what that time was. And so we could calculate what the V0 should be, the initial speed, just solve for it right here in this equation. It's going to be the range divided by t. How far it goes divided by how long it takes to go there. That would give us the initial speed. However, we don't have a stopwatch. All we can do is make measurements of length. That is, we can measure the horizontal range, and we can measure the initial height, y0. Okay, so we've measured the initial height too. Let's see, so we have an extra piece of information. Can we use that to figure out what the time of flight is? Yes, we can, from our kinetic description. So here we have this equation right here for the y position. Okay, so y will be equal to, okay, y0, wherever it is when you start the clock, plus Vy0t, right here, Vy0t. But the Vy0, notice, in this particular case is 0. There is no Vy0. So that term is 0. And then they'll just be minus 1/2 gt squared. Now when t is equal to the time of flight, what happens? Okay, so these two equations right here, this equation for x and this equation for y, these will describe the position of our projectile versus time for all time starting from 0 when we start the clock. We start the clock at 0 to t equals time of flight. So it starts from 0, it'll describe the position any time to when it hits the ground. Then after it hits the ground, then it just stays there. So for times after that, it's just going to be right here at this spot. Y equals 0, x equals a range. At t equals the time of flight, and that's what we're going to consider is happening right here. T is just equal to the time of flight. What can you say about y? Right at that time, y is equal to 0. Right? Because we've defined it that way. The ground is 0. Here's y is equal to 0 right here on the ground. So at t equal time of flight, which is what we're considering to be the case here, we're going to have 0 will be equal to y0 minus 1/2 gt squared. Okay, and this is typical for how you would solve projectile motion problems. First thing you'll do is go look and see, can I simplify any of these equations? One thing you can often do is take x0 equal to 0, right? Just define your axis in such a way that you shoot the projectile from a position x equals 0. Okay, so you can usually make this simplification. Now, if it's being shot horizontally, then there is no initial component of velocity in the y direction, like this case, and you can also set this term equal to 0. So here you see we've simplified our position equations a little bit here, as you see. So for any typical projectile motion problem, this is the way I like to proceed. I go and see if I can make any simplifications in these equations. Sometimes you can. If it's at an angle shooting, then you can't really do too much. Then I rewrite the equations. Then I consider t equal time of flight. And at t equal time of flight, then y is going to be equal to 0. And so you're going to get another equation here where you simplify it a little bit. And then you can see in this case, okay, what are we looking for here? Well, we said over here, we know the range. We measured that, right? We took our tape measure, measured the range, say 16.2 meters or whatever, after we fired it. And so if we knew the time of flight, we could just stick that in there now and figure out what the initial speed should be. Okay, but look over here. What do we know over here? We know this initial height because we can also measure that. Just take our tape measure and measure it. We know gravity, right? Gravity is always 9.8 meters per second squared, acceleration due to gravity. So that's known. So the only unknown over here actually is the t time of flight. So let's just solve for it. It's going to be 2y0 divided by g square root. Okay, great. So we have that, and then we could put that in. So now everything's known here. G is known. The y0 is known. We measure that. Just substitute that in for v0. Okay, we're going to get v0 is equal to the measured range divided by 2y0 over g square root, which we could rewrite, and we could get it like this. G over 2y0 square root times the range. And that's what we're going to use to verify the range, experimentally verify the range. We're actually just going to take our data, so for given initial heights and measured ranges, we're going to calculate the initial speed using Excel. Let's look at the handout. So right at the top, here's the kinetic description of projectile motion, and here's a little picture of some guy like William Tell or an archer here shooting an arrow. So that gives us, lays out the initial velocity vector for it. It shows how we can resolve the x and y components of that vector. Our first job is to experimentally verify that the FET cannon has the initial speed as advertised, and that initial speed is compatible with this kinetic description of projectile motion. So let's see how we're going to do that. All right, and here's the equation we derived. So here I derive it again in the handout, and this is the equation for the initial speed of the projectile shot from the FET cannon, or any projectile. Okay, so that gives you its initial speed assuming that you shoot it at a 0-degree launch angle, that is, we fire it horizontally, and then in that case, the initial speed is given by the range, how far it goes over the time of flight, how long it takes to go there, and here that equation is going to be that range times this stuff right here, g over 2y0. So let's look at how we're going to collect our data and then use this equation to verify the initial speed corresponding to shots fired. So we're going to go to the website, launch a FETSIM, click on motion to narrow the choices, select the projectile motion sim, launch that, and then pick lab. And for you, you're going to use the tank shell. So when you do the experiment, select tank shell. But for this example, I'm just going to stick with the cannonball right here and use the default initial speed. You could change the initial speed with this toggle over here. We're just going to use the default. Remember, also select air resistance. And then what we're going to do is take them all the way up to 15 meters. And so you don't need to measure the tape measure for the vertical component because it just tells you what it is right here. It's at a height of 15 meters. And so now we shoot and then measure the range. So we just shot it from a height of 15 meters. I'm going to just have to eyeball this right to the middle down here. Set him, put this position down there right at the vertical drop. This little X marks a spot. That's where X is equal to 0 meters. And then drag this over here. And we're going to go ahead and measure our range. At 15 meters, shot from a 0 angle, I got 31.22 meters for the range. And then enter that in a spreadsheet right over here. So this is the spreadsheet that has the values, my experimental data that I collected when I did this experiment with the cannonball. Hopefully you can read it, but anyway, I can tell you what so at initial height of 15, y0 is equal to 15 meters, I measured the range with that tape measure to be 31.28 meters. And then, as you're going to do, I just lowered the height step by step. We'll go back and look at how I did that in just a second, but there's no big deal to it really. You just keep lowering that height down. It lowers naturally in 1 meter steps, so you shoot at 15, measure the range, lower the height to 14, shoot it, measure that range. At 14 I measured 30.2, I lowered to 13 and measured 29.19 meters as a range, and so on. Then I use that formula, and here I've entered it again in the spreadsheet, that formula r times the square root of g over 2y0, and entered that in right here. Now let's look here how I did it. So right here I entered that formula in. You enter an equal sign to let Excel know you want to calculate a formula. That's what that equal sign does. And here, I'll just re-enter it. Let's just redo it. So what you do is you enter an equal sign, lets Excel know you want to calculate a formula. Then it's times r, okay, that's the measured range. So I'll click the cell with the measured range in it. Okay, that times, then it's the square root. Start typing square root. Once you see it, you can double click it. That's how I like to do. And then I'm just going to follow the formula. Formula says to use G. G is 9.8. Or notice I have it over here in a cell. I actually have G in a cell. Here I'm using it to one more decimal place, or entering it to one more decimal place, 9.81. So actually, I'm just going to click on the cell that has that value. I think I like to do it that way this time. Then now that is times, and it's going to be times 2y0. Here I have to enter an open paren because it's all G is all divided by 2 times y0. So it's 2, I have to enter that myself, 2 times y0 is, here's the initial height, times that, then I close paren. Let's see what I get. Oh, what did I do wrong? Square root. Oh, divided by. Okay, there we go. Alright, so that's the formula. Well, let's see what happens now. If I fill that down, what's going to happen? I could grab this, and I can use Control D to fill down, or I've now learned this trick where if that crosshair, that black crosshair is on like that, it will automatically fill down. And what happened? Everything just got eradicated. Let's see, because what's happening? See, let's see. So here it's E3. So it's B3 times the square root of E3. Where's E3? E3 is right there. But then down one cell, it goes, okay, down one cell, it goes square root of E4. So it looks for whatever's in E4. At that cell, there's nothing. So it thinks zero's in there, nothing is 0, so it evaluates to 0. That's not what we want, right? We always want this first value here, whatever's in E3, to be gravity. So how do I fix that? Lock cells. Okay, we've done this before, but I'm just showing you again. So now what I want to do is, if I put a $ in front of the E, that locks on the column. Come back over here. And then if I put a $ in front of the 3, that locks on the row. So I lock on column and row. That completely locks the cell. I think here actually all we would have to do would be to lock the row. I think that would work just fine in this case, but I like to lock everything. I don't know why. So we enter that in. Notice it doesn't change anything there. Okay, that's all the same. But now when we fill down, kabing bang, we get the answer back again as we wanted. And here that seems to be an embarrassing number of decimal places, so I could use this decreased decimal thing to lower them down. And then we can calculate the average value of our speed. So that here would be the average of all this stuff, the average of everything in here in this range. So you can see that function is the average. And we've done this before, so I'm just going to speed right through this. The standard deviation, and then from the standard, and again it's from the standard deviation is for the same data, all this data, all these, here's the data, and here's the speeds we calculated from those data. And that's the standard deviation of the speeds. And then the standard error is the standard deviation divided by the square root of the number of data points. In this case, the number of data points should be, again, just to make sure, I can insert a column, call this run 1, 2. I'll make this run 1. Call that equal to whatever's above it plus 1, and fill that down. Okay, so it's 15 data points. Just wanted to make sure about that in case I'm, if I don't want to even bother with counting. So I know there's 15 data points. So the standard error is the standard deviation divided by the square root of data points in your sample. In that case, is 15. So it's divided by square root of 15. So that's 0.02. And that allows us to report our overall experimental result for the speed calculated by using these measured heights and length, initial height and horizontal range in the kinetic description of the motion, and then we get, this is our average value, so we can report the result as the experimentally found speed is this average value plus or minus the standard error, 0.02. And here you could see, well, I guess I could have put, I could have left this 9.1 like that, plus or minus 0.02, because this 0.02 doesn't really swamp this 1 here in the hundredths decimal place. But anyhow, we can see that that value, 17.91 plus or minus 0.02 meters per second, within our error bar, lies within the expected range of the speed being 18 meters per second, the expected speed. And here's a percent discrepancy. You can see how I calculated that. It's the expected speed, 18, minus the average, here's in D20, divided by the expected speed, 18. So it's x best minus x over x best. And then display that as a percent by clicking this percent toggle right there. Okay, so that's our experimentally calculated speed, initial speed of the FET cannon. And we can see that we're matching real well, right up to 0.5% discrepancy. So the experimentally calculated value matches the experimentally measured value within 0.5%. Okay, good. Let's go back to the handout and look at what they want us to do for part 2 of this experiment. So in part 1, we just verified that the speed of the cannon is 18 meters per second. So we verified that experimentally, that it's compatible with the kinetic description. Now in this next part, we want to verify that the kinetic description gives the horizontal range for shots fired at an angle. So before we just fired shots at an angle of 0 or horizontally. Now we're going to vary the angle. We're going to vary the angle. So let's see what they ask us to do here. So we're going to collect data by fixing the height at 5 meters, so we're not going to change the height anymore. We're just going to set it to 5 meters, and then we're going to keep the default speed 18 meters per second for shots fired, but we're going to vary the angle that we shoot the cannon at from 0 to 70 degrees in steps of 5 degrees. And then we're going to measure the range of shots fired at those different angles, and we're going to collect that data in our spreadsheet, which is going to allow us to make a spreadsheet that looks like this. Okay, so let's see what we're going to do. Let's go over to our FETSIM and see what we're going to do here. So to follow the spreadsheet that we have, what we can do is we can just we can start off with we're going to set it to 5 meters. That's what it says to do. Set the thing to 5 meters. Clear this off, and we're going to leave the speed like that. We're going to start off at an angle of 0, and then start shooting it, measuring the range. So here I'm at 5 meters, got an angle of 0. Oh, I don't want to use that one. I'm going to use a tape measure. I fired 18.02 meters is the range. Go to angle 5, shoot. 21.06 meters is the range. So I'll just keep shooting. Then let's say I'll be getting up here to bigger angles. Let's say when I get to 30, see what happens. It goes off screen. Okay, you can see in that case what you're going to need to do is hit this minus right there to zoom out. Now we can go ahead and measure again. So at 30 degrees, 35.15 meters. And I skipped a bunch of degrees in here. Right, I went so here I went 0, 5, and then I skipped to 30. But what you want to do is go 0, 5, 10, 15, 20, 25, 30, all the way up to your final shot. You shoot at 70. I measure that guy. He'll be something like 22.5 or whatever you get. So now let's look at the spreadsheet, and here's the data I collected for that. Okay, so my angle is 0. I measured about 18.17. Then I went to 5 and measured about 21.2, and so on. At 30 I had like that, and you can see at 70, something like that. Okay, we'll come back to this in a second. Let's go back to the handout real quick. That handout, if you look at that, you'll see we calculate what the range should be from the kinetic description. Okay, and the range from the kinetic description will turn out to be this formula right here. Is kind of it's kind of big, but it's not that bad. And we're actually going to be entering that formula in Excel. We're going to use this to calculate the range directly and then verify that it's compatible with the range that we measure with a tape measure. If this kinetic description of the motion is valid, then the range we calculate should be equal to the range we measure up to experimental error. They should give you basically the same thing, and this is the calculated value. What I want to do now is go through and see how we actually calculated that, just to get a little practice. Okay, so let's do that next. Alright, so in part 2 of the lab, we're going to be assuming that now the initial speed we verified is given. So we're given the initial speed, and we want to verify that with that initial speed we can calculate the range for a fix. And here we're going to be fixing the initial height, so we're going to say y0 is equal to 5 meters, and that's fixed. So we're going to fix the initial height, we fixed the initial speed, but now we're going to be varying the angles that we fire the cannon, and we're going to check that the kinetic description of projectile motion allows us to calculate the range, and when we can verify that calculated range experimentally. So again, we can shoot the cannon at some angle, whatever angle we like. We're going to be firing it from 0 to 70 in steps of 5 degrees. So we fire it, so this is our initial speed. It's a vector we fire it at. And again, we want to resolve that into components, x and y components, that initial angle. Okay, so let's look at how we're going to calculate the range from the kinetic description. Well, again, we're going to let x0 equal to 0. So we do have this simplification right here. So x is equal to vx0t. So that's going to hold. Again, so we'll have x equal to vx0t. And again, if t were to be equal to the time of flight, and can we calculate the x0? Yeah, we can, because we're given the angle, right? So these are fixed, but theta is given. We're going to start 0, 5, dot dot dot, all the way to 70 degrees. So for each given angle, we can figure out what the components of the velocity are in the x and y direction, x and y components from this formula here. But again, okay, so we shoot this thing, okay, and it's going to fire out over here, land over here at x equal to the range. So we're given the initial speed, given the angle, so we'll know what the Vx0 is. If we knew what the time of flight was, again, we could just stick that right in here and calculate the range. So how do we get the time of flight? Well, we get it pretty much the same way we did last time. So here we have this equation right here. That's y is equal to y0 plus vy0t. Now, this time, since the angle is not necessarily 0, like when it's 5 degrees and so on up to 70, the angle's not 0. In that case, there is some initial y component of velocity. So we can't just set that equal to 0 right there. So that gives us a little bit of extra work to do. So we got vy0 t minus 1/2 gt squared. That is the equation that gives us the height of the projectile at any given time. It's position y, its height y at any given time between 0 and the time of flight. 0, it'll be right here. Then as time goes on, this equation will tell you where it is at any given time, all the way until it lands down here at the time of flight, at which point y will be equal to 0. So here again, we're going to say, okay, we're going to think of t equal to the time of flight. That's how we want to think of it in this equation. And at that time, y is equal to 0. So this particular equation right here, we have all this stuff then is equal to 0. Everything here. And that is a quadratic equation in the unknown t, because everything else here is known, right? The initial height is known. The vy0 is known because, well, we know the initial speed and we know the initial angle. So we calculate the vy0 from this equation right here. It's v0 sine theta. So we can solve this for the time. However, it's a quadratic equation. That makes it a little bit more of a challenge. So what can I do here to solve this thing? I'm going to do this in steps. So I'm going to solve this for the time, and it's a quadratic equation. So what am I going to do here? I think I'm going to multiply this equation through by -2 and see what that does for me, and rearrange some terms here. So if I multiply by -2, I'm going to get gt squared minus 2 times 1/2 is a +1. Then I'll put this term next. It's going to be minus 2 vy0 and then minus 2 y0 all equal to 0. I multiply both sides of the equation by -2, but 0 times anything is 0. Now why did I do this? Well, because I'm going to look at the form of the quadratic equation. So the form of the quadratic equation is ax squared plus bx plus c equals 0, and in that case x will be equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. That's the quadratic equation. Okay, so we're just going to have to use this to solve for t. So I'm going to come over this way with t, plugging into the quadratic equation. So let's see how we do this. So follow this pattern here. Okay, minus b. So minus b, the term standing in for that is, or the term standing in for b is minus 2 vy0. So minus that is going to be minus a minus is just going to be 2 vy0 plus 2 vy0, because it's minus b, but b is minus 2 vy0, and minus a minus is a plus. Then it's going to be plus or minus, okay, square root of a bunch of stuff. Okay, this thing squared, 2 vy0 squared minus 4. Now what's a? A is this term right here. G is standing in for a, minus 4 ac. What is c? C is minus 2 y0. That is c. Okay, and it's the square root of all this stuff, all divided by 2a. 2a is 2g. Okay, so let's see what we got here. Okay, I'm going to go, and this is This is all what t is equal to. Now what I'm going to do is simplify this thing. Well, one thing I could do is, okay, simplify and place it here. I'll make this a plus by just knocking this one out. Minus times a minus is a plus. So I just did that right away right there. So I just multiplied those two minus signs through by each other and got a plus here. And now, well, I'm going to divide both sides by 2g. Okay, so I'm going to get t. I'm going to divide the 2g into every term here. So 2g divided into this first term just gives me vy0 over g. Then I have plus and minus. And then here I'm going to have the square root, a bunch of stuff. Now 2g under the radical becomes 2g squared. Then I can move it inside this term with the parentheses. 2g, I can move it inside this term with the parentheses, and then it'll become squared inside these parentheses. It has to be squared under the radical if I move it under the radical. And then this parentheses will handle that squared. And then inside there, the 2's will cancel, and I'm going to end up with vy0 over g squared. I just moved this 2g up. I tucked it up under here with the 2 vy0, and then under the radical it's simplified to vy0 over g, all squared. You should check that on your own just to make sure you agree with me that that's true. It is true. Now in here, what will happen? Here I'm going to have 2g is being squared. So it's going to be, I could also view that as a 4g squared. So all this stuff, if I move this term under the radical, will be like 4g times 2y0 all divided by this all squared, which would be 4g squared. That 4 will cancel. One of the g's will cancel, and I'll just be left with a g in the bottom. And so it's going to be 2y0 divided by g, and raise that to the 1/2. That's the same thing as taking square root. Now this is the time of flight, and it is the time of flight as long as I take the plus sign. Here I have to take the plus sign in the radical, and you can see why. If I took the minus sign, if I were to take the minus sign as one of the two roots, one of the two possible answers that solves this quadratic equation, what would happen? Notice here I have vy0 divided by g, and in the radical here I have vy0 divided by g squared. When I take the square root of that, then it would just be the same size as this. And so let's say y0 was 0. This whole term was 0. Then if I were to take the minus sign, then the time I could get would be 0, right? This would be this stuff squared, square root, we'll just leave this stuff again. Then if I subtracted it from this, since that would be the same thing, would all come out to 0. Now anything I add over here, so say if y0 is not 0, anything I add over here makes all this stuff bigger. So when I take the square root of it, all this stuff now would be bigger than whatever this was. And if this was a minus sign here, and I took it away, all this stuff from this stuff, if this stuff is bigger, then I would get an overall minus as my answer, would have a value of some minus number, and that would give me a minus time. But the time can't be minus from when we shot it. Remember, we're counting time forward from after we shoot the projectile. So a minus time would be unphysical, wouldn't make any sense. So we have to take the plus sign. Okay, so all that just to say that I erased the minus sign right there, and this is the value I want. Okay, and that is the time of flight. So notice that the range then will be given by, so x is equal to vx0 times that time of flight. So when x is equal to the range, t is equal to the time of flight. It's equal to, okay, vx0t, where t is all this stuff. So that means that the range has to be all this t times vx0. So, and I could just multiply both sides of this equation by vx0, and I'll get vy0 plus times vx0 over g plus, okay, and inside the radical, vx0 has to be squared. Here it's squared. And this all has to be raised to the 1/2 power, or take the square root. Take the square root of all this stuff. And that is the answer. That is the range that we were looking for. to calculate. And so what we can do now is enter this formula in Excel. We can count, so for the given speed 18 and given angles, we can just use Excel just to go ahead and calculate this stuff for us. The initial velocity components, x and y components of initial velocity. We're going to be measuring the y0. Well, the y0, we just fix that. We know what it is, we measure it, but we don't change the value. Then the range, which we're going to be verifying, we measure. And we can calculate what the range should be from the kinetic description with this rather, well, I don't want to say monstrous, but it's not a trivial formula. But let's go ahead and look at how we can do that in Excel. So let's finish off part 2 of this lab looking at how we can do the calculations in Excel. So here's my Excel spreadsheet where I have trial 1 through 15 for angles ranging from 0, 5, 10, all the way down to 70 degrees. Then in this cell here I calculate what the initial velocity in the x direction, or the initial x component of velocity, is. Just from the formula, just look at the formula for the kinetic description, that velocity is the speed, 18 meters per second, times the angle that it gets, times the cosine of the angle it's fired at. Notice how I do this here. I have my fixed data that we're going to be using for this all over here highlighted in blue. You don't have to highlight it in blue. I just did that to emphasize the fact that it is fixed data. It's data that's not changing or staying constant throughout the experiment. So those fixed data are the acceleration due to gravity, 9.81 meters per second, the fixed initial height that we fire the cannon at, 5 meters, and the initial speed we're shooting at, 18 meters per second. And that initial speed, okay, that's right here. I use that in this calculation. See this K3, this is the K3 cell. It's got the 18 in there. And of course I want to fix it by locking on the cell. So the dollar sign in front of the K, I added that myself. And the dollar sign in front of the 3, that fixes on, if I put it in front of the K, it fixes on the column. If I put it in front of the 3, that fixes on the row. Putting it in both fixes the cell. So that locks that cell. And cosine of the angle, now here the angle is in degrees, but Excel, for its cosine and sine functions, its trig functions, Excel likes the angles all in radians. Luckily for us, Excel has this neat function, radians. You see how to calculate this. So I'll just do this myself one time here for you. So I go equal to, click on the cell over here, K3, times, so I start typing, I want a cosine. Let's see, I got the cosine down here, click on that, and then now if I just click on the angle over here, that would work for 0 because 0 degrees is equal to 0 radians, but for any other angles going up here, Excel wants the angle in radians. So how do I get that? I use this radians function, double click on it, double click the cell with the angle in it, then close paren, and here enter, and for this first one it would work fine, but you could see, let's say if I fill this down, it's going to mess everything up. Control D here, I just messed up all my data, right, because I needed to lock on this cell. I need to lock on this K cell, so put a dollar sign there, put a dollar sign there, so you may be getting used to that now. Now when I fill this down, I'll recover everything, and notice it replotted everything, and Excel, you definitely want to be using the power of Excel. If you're using your calculator for all this stuff, it's going to be driving you crazy. It's too much work. Use Excel. Okay, so I entered that there. Okay, so here's the Vy0. I get that. The difference is I need to use the sine function to calculate Vy0. The calculated range, here, this is that formula that we just derived. And it's also written down for us in the handout. So that's the formula. I just went ahead and just entered it in here. You just have to work through here to see that all these terms correspond to the terms in that formula. They're just where the values are. Right? So I'll let you work through that. So that's the calculated range. You enter that formula. Notice that everything that's over here in the I, J, and K3 cells right down here, that's fixed data. So we have to lock on all those values in this formula to fill it down as we want to do. We want to, once we get this thing right, we want to fill that down. You just enter it, you get it right one time, you fill that thing down, and it's going to nail it for you, do all the work. So that's definitely what you want. Here, these are just the tape measured values of the range that I measured directly in FET. This is the discrepancy. Here I calculated it from, okay, so it's the calculated value minus the measured value divided by the calculated value expressed as a percent. So you can see that right there. That's the percent discrepancy between the calculated and measured value of the range for each of these trials. And you can just fill that down, and then the average discrepancy turned out to be 1%. So it's pretty close. That 1% could probably be due to air resistance. We can see that my measured ranges are typically a little bit less than the calculated ranges. So the kinetic description predicts just a little bit further of a range than what I measure typically, or yeah, in every case, because otherwise there'd be a minus sign. If one of these turned out to be more, then it would give a minus sign here the way I did the formula. So that is consistent with air resistance, right? We would expect air resistance to reduce the range just a little bit, and so the measured ranges should be reduced a little bit from the calculated values, and that's what we see here. So I would go ahead and say, that's probably has something to do with the air resistance. But it's not a big deal for a cannonball. You can see you can treat the cannonball up to 1% discrepancy as being described by the kinetic description of projectile motion, neglecting air resistance. So basically, cannonballs don't have much air resistance, what we're saying there. And tank shells, even less. You should, with your tank shell, I'm going to imagine you're going to have even less discrepancy between the calculated and measured ranges. Now this last thing here is a nice way, this graph right here is a nice way to visualize your data once you get it. And I won't go through the whole process of how you get this graph, but I'll just start you off here. I'll do one shot on how you could cook up a graph like this. There's I won't go through everything here, like these axis titles and these data series titles. I'll let you figure out, play around with that. That's how I figure this stuff out. I just play around and click around. I mean, there's stuff here you can use to format it, chart elements, chart styles. I mostly use this chart element stuff. I'd say go ahead and figure that out. Mostly what I'm looking for you to do is just plot your range versus angle data to compare your data in a plot like this. You can see, so it looks pretty nice like this. I'll show you how to plot it, and then we'll come back and talk about it just for a second. So to plot this data, what you want to do in this case is just select an empty cell, because right now your x values or your horizontal values and your y values, that is your horizontal values are the angles, and your y values or your vertical values on the plot are the ranges. Those are not right next to each other. So the natural native format for scatter plotting like this in Excel is to have the x values on the left and the y values on the right in columns next to each other. Here it's not like that, so you need to select the values by hand. So what you do in that case is get an empty cell, go over to the Insert tab, go over here to Charts, get yourself a scatter plot, then you can see it's blank. Right click inside the scatter plot, do Select Data, then you're going to go ahead and click Add, and here you're going to manually specify. You could give a name to it right here if you wanted, whatever you want to call it. Like you could call it, here we could call it experimental. And then we go, okay, X series values. Those are going to be the angles. Y series values. Notice when I click on that icon, this colory icon over there a second ago, it already highlighted this weird stuff in here, this parentheses 1 thing, so we want to overstrike that. Now get the Y values. That's going to be, okay, I said experimental, so I'll just click these ones. Okay, so there's the experimental range versus angle. And if I want to add the other ones to this, then I go over here, right click again, select data, do add. Here I'll call this one calculated. X values, in this case the X values are the same. They're just the angles. But the y values, oh, calculated, what did I do? I went too fast. The y values are going to be a little bit different because here they're the calculated values of the range. Okay, and so this chart you can see is the same as this chart. This one's just a little more formatted up. But, you know, if you included one that looked like that, I guess, well, yeah, go ahead and play around with it and see if you can format it a little bit so at least you identify which which data series corresponds to the measured and experimental. Here my blue ones correspond to calculated and my orange ones correspond to measured. So over here I think it might be vice versa. But anyway, go ahead and try to label those so we can differentiate between the calculated values and the measured values on your plot. Okay, I think that wraps it up. I think you should go ahead and be able to finish the lab from there. Try to enjoy it as best you can, and I'll see you on the next one.